Good morning. Now we are discussing about the types of moduli of elasticity. I have three different moduli of elasticity. The Young's modulus is the first one among the three. Let us study one by one in detail. Young's modulus is defined as the ratio of longitudinal stress to the longitudinal strain within the elastic limit. And it is expressed over here. You can see here Young's modulus is the ratio of longitudinal stress to the longitudinal strain within the elastic limit. Beyond the elastic limit, this does not hold good. For this, we are considering a uniform wire having a length L and area of cross section A. A will be equal to pi r square, where r will be radius of the wire. And this wire is subjected to a force F along the length of the wire. Because of the force which is acting along the length of the wire has been extended, and therefore the increase in length of the wire is taken as equal to delta L. Now, we know that Young's modulus is longitudinal stress by longitudinal strain, but longitudinal stress is the force applied per unit area. Force per unit area gives longitudinal stress, and ratio of change in length to the original length, or the ratio of increase in length to the original length, gives the longitudinal strain. Substituting these two in the expression below, we get Q is used to represent Young's modulus. Q is equal to F by A whole divided by delta L by L. Or rewriting, we get FL divided by A delta L. Or if A is equal to pi r square, where r is radius of the wire, then Q become equal to FL by pi r square into delta L. In the above expression, if we take L is equal to 1 meter and A equals 1 meter square, and also delta L is equal to 1 meter, then Q will become equal to F. Hence, Young's modulus of the material of the wire is defined as the force required to double the length of the wire of unit area of cross section. Young's modulus is defined as the force which is required to double the length of the wire of unit area of cross section. This is how we define Young's modulus. The SI unit used to measure Young's modulus is Newton per meter square, and this Young's modulus is applicable only to solids, and that too when the deformation produced by the external force is only along one dimension. Young's modulus can be applied only to solids, that too when the deformation is in one dimension. This is about Young's modulus. Now coming to the rigidity modulus, represented by the symbol eta. And this rigidity modulus is defined as the ratio of tangential stress to the shearing strain. The ratio of tangential stress to the shearing strain within the elastic limit is called rigidity modulus. In order to explain this rigidity modulus, we consider a cube in which the lower surface ABCD is fixed, whereas we apply a tangential force on the surface EFGH. You can see here, EFGH is the upper surface of the cube over which we are applying a tangential force capital F. If surface area of the cube is A, since it is a cube, the surface area of each side is taken as equal to A, and if theta is the angle of shear, so you can see here, then rigidity modulus is given by definition, it is tangential stress by shearing strain, or eta is equal to tangential stress is F by A whole divided by shearing strain is theta, or it is equal to F by A into theta. F by A into theta. Right? Now, because of this tangential force, the shape of the cube gets changed. So, the lower surface is fixed. As the tangential force is applied on the upper surface, each layer of the cube above ABCD gets displaced laterally, and that is given by the shearing strength theta, because of which it results in the change in the shape of the body. Now, shearing strain is displacement of a plane divided by total distance from the fixed plane. Shearing strain can be evaluated like this. Shearing strain is represented by theta, this one, or tan theta, and that is equal to displacement of the plane EFGH, and displacement of this plane is E dash or HH dash or FF dash or GG dash, one and the same. I took it as E dash, divided by distance from the fixed plane. Distance of this plane from the fixed plane is EA, or that will be equal to L. And this E dash is taken as delta L, EA is L, we know that, and shearing strain is tan theta. Tan theta is opposite by adjacent. Therefore, tan theta is E dash by EA. For small angles, tan theta will be taken as equal to theta. Therefore, theta is E dash by EA or delta L by L. Therefore, eta becomes F by A into theta become F by A into delta L by L, or it is FL by A into delta L. FL by A into delta L. And this is about the rigidity modulus. Now coming to the bulk modulus, represented by the symbol kappa. It is defined as, the bulk modulus is defined as the ratio of volume stress to the volume strain within the elastic limit. The ratio of volume stress to volume strain within the elastic limit is called bulk modulus. In order to study bulk modulus, we consider either a cube or a sphere having a volume V. We now consider a force F acting normally all over the surface of either the sphere or cube. Since the force is acting perpendicular to the surface, number of forces will be acting on different surfaces, because of which the volume of cube or sphere gets decreased, and the decrease in volume is given by delta V, and the force per unit area which is acting on the surface is called pressure. Under this pressure, volume stress is F by A, that is nothing but pressure, and volume strain is minus delta V by V, minus because the volume is decreasing because of the pressure. Therefore, bulk modulus kappa becomes equal to F by A whole divided by minus delta V by V, or minus FV by A delta V, or it is minus PV by delta V. P is nothing but F by A. This is about the bulk modulus. Now coming to the Poisson's ratio. When a force acts along a body in one dimension, there is an extension of the body in that particular direction, and the dimension perpendicular to it will be decreased. For example, if we consider a wire which is one end of which is fixed to a rigid support and the other free end is subjected to a load, because of which the length of the wire gets increased. As the length of the wire gets increased, the radius of the wire, or in other words, the area of cross section of the wire will be decreased, and vice versa. Now, the ratio of change in dimension to the original dimension along the direction of the force is called longitudinal strain. Similarly, the ratio of change in dimension to the original dimension perpendicular to the direction of force is called lateral strain. Longitudinal strain will be increased when the force is acting along the length of the wire, whereas the lateral strain will be decreased. Longitudinal strain is nothing but this one. Change in length by original length is longitudinal strain. The length will be increased due to the force acting along its length. The lateral strain will be decreased because as the wire gets elongated, the radius of the wire will be decreased. The wire becomes more and more thin. Now the ratio of lateral strain to the longitudinal strain within the elastic limit is called Poisson's ratio. Poisson's ratio is defined as the ratio of lateral strain to the longitudinal strain within elastic limit. And longitudinal strain is represented by alpha, that is equal to delta L by L, increase in length by original length. Lateral strain beta is represented by the ratio of change in dimension to the original dimension perpendicular to the force, or in this case it is the decrease in radius to the original radius. Poisson's ratio is represented by the symbol sigma, that is equal to lateral strain by longitudinal strain, or that is lateral contraction by longitudinal elongation. This is about the Poisson's ratio. Thank you.